Hello, I'm Dr. Dupre, and in this section we're going to discuss double integrals and volume. The double integral in the first place is what we use to compute volume in 3 dimensions. For instance, if I have a domain in the xy plane and I have the graph of a function which is non-negative and I'm interested in finding the volume trapped underneath that surface, that can be computed as the double integral over this region in the plane of the function of 2 variables. And that would give us an expression which we would denote this way. Here R is the region over which we're integrating, and here's the double integral of the function f of xy against area dA. Now, in order to accomplish this, what we have is a theorem called Frobenius Theorem, which is the real workhorse of multiple integrals in all dimensions. So it's illustrated best in 2 dimensions, and it really works in any number of dimensions. But the idea is that we want to take this double integral and slice it up into integrals along one direction and then integrate the results of the integrals. So let's look at this in more detail. First off, what we have is this big long equation here, and this is on the left an integral of what's inside an integral. What we call this is an iterated integral or repeated integral, and that repeated integral is equal to the double integral, and over here I have another way of doing it. And Frobenius theorem tells us in particular that either of these ways gives us the double integral, and it also tells us in particular that the double integral does break down as an iterated integral. So let's look at the picture. Now in detail, here the blue-green curve is meant to represent a surface here, which is the graph of the function z equal f of x comma y. Now, in fact, that function need not be non-negative, and the double integral of the function still has meaning. For instance, as you see this picture, what we've got here is a depression in the surface which actually pokes down below the xy plane, which I've indicated with little kind of dotted curve here, outlining the way the surface dips down below the xy plane. The yellow curve is the boundary of the region capital R over which we want to integrate the function f of xy. Now, one way to do this, for instance, is for each value of y, we can hold y fixed momentarily, imagine that, and then we could integrate in the x direction. So if I hold y fixed, notice for a fixed value of y, as x varies, we get a curve through the surface, and in effect what I could try to do is integrate that function f of xy for y fixed against x, and what I have to do is integrate it from this lower value of x to this upper value of x. Notice that these values of the limiting values of x that I have to integrate between are themselves going to have to vary with y. In other words, if I take a y there, the range of integration for x is different than over here. And in order to describe that, what I have to do is look at the boundary of the region and describe that with curves. Now, the best way to do this in optimal situations is where those curves can be themselves described as graphs of functions. In that case, we say the region is simple with respect to y, or y simple. That is, as y varies from the leftmost point of the region to the rightmost point of the region, we have the upper values of x being a function x equal h2 of y, and likewise along these lower values of x, x is another function h1 of y. And so for each fixed value of y, when I look inside this big pair of brackets here, what I'm doing is I'm integrating f of xy with y fixed from h1 of y to h2 of y. And so that would sort of be represented in this case. You can think of it as the area under that little black curve there, which I've cross-hatched there. And so you can see that for each value of y, I get the area under the curve, or in the case where the curve passes below the xy plane, it'll be, in effect, the integral of f of xy. In any case, as y varies, that integral varies. And so in order to accomplish the entire integration, I then integrate this function of y. You see, that whole result only depends on the y. And so now I let the y vary and integrate from the leftmost value of y to the rightmost value, which I've denoted by c and d. So the definite integral from c to d of this integral from h1 of y to h2 of y of f of xy dx, then integrated against dy, is what we then get as a value for this double integral. Now let's look at this region in the xy plane and concentrate on it for a minute. And so I'm now going to take this region and put it up here on the board in a way that we're looking right down on the xy plane. So what we were doing before was integrating from one part of the curve parallel to the x-axis, along the x direction, which I've denoted with the dotted red line. But suppose instead we wanted to hold the x value fixed and integrate in the y direction. Well, we could look at this curve, which is the boundary of the region R again, and say, well, let's try to represent the lower part as a function y equals g1 of x and the upper part as a curve y equals g2 of x. And so here we've got the upper part of the curve, and notice right here we have sort of a break point. The lower part is the graph of a function, the upper part is the graph of a function. The leftmost extent is a and the rightmost extent is b. So in this case we say, well, the region is x simple. And so consequently we can turn the process around. So in this case, you see, for each fixed value of x, we're now going to integrate in the y direction. And what's the range of values of y? For a fixed x, it goes from g1 of x up to g2 of x. And so now we have the integral from g1 of x to g2 of x of f of xy dy. And notice once that integration is done, the result is a function of x alone. And so consequently, what we've got to integrate now is this complicated, possibly, function of x from a to b. And that gives us another way of computing the double integral. Frobenius theorem then says if either one of those exists, then it gives the value of the double integral. In other words, if you can set it up in either one of those ways, that's going to give the value of the double integral. And if both ways can be set up, then both ways are in fact equal to the double integral, so they have to be equal to each other in particular. So Frobenius theorem then is the real workhorse of multiple integration, because in the calculations that we'll be doing, we'll virtually always use Frobenius theorem and iterated integration to accomplish multiple integrals. Now let's look at a specific example of how we calculate. Let's calculate the double integral over the region R of x squared plus y cubed dA, where R is the region 0 less than or equal to x less than or equal to 2, and y between 0 and 1. Well, for instance, the x varies from 0 to 2. And when I look at this, remember the outer limits are going for the last variable here. The limits on the outer integral go with that variable. And these limits, 0 to 1, are for the y variable. And see, y is restricted to be between 0 and 1. So, of course, in this case, our region is just a rectangle. In the xy plane, it's simply y has height 1 is allowed, and x can go over 2. And so it's just this little rectangle in the xy plane. Now, in order to accomplish that, then, we simply concentrate on the inner integral, and we think of x as a constant. The sort of the reverse of partial differentiation. This is like partial anti-differentiation. So I'm going to anti-differentiate with respect to y, thinking of x as merely constant, because remember, while we do that slice of the integral, we're holding x fixed. And so the antiderivative of x squared y with respect to y is the antiderivative of x squared with respect to y is x squared y. The antiderivative of y cubed with respect to y is y to the 4th over 4. And so that's to be integrated from y equals 0 to y equal 1. Now, notice when we ordinarily put our limits of integration on the antiderivative after evaluating an integral, after we anti-differentiate and we put our limits on, we'll just put the numbers there. But when we're doing multiple integrals, it's always safest to actually put the variable that you integrated in the values of the limits, so that when you actually plug in, you'll remember which is to be plugged in. In other words, if I just put 0 to 1 there, I might accidentally start putting in the values into the x variable, say. But now I can easily remember I've just integrated with respect to y, and that's to be evaluated from y equals 0 to y equals 1. Well, when I put y equals 1, notice this term becomes x squared, and this term becomes 1/4. If I put y equals 0, I have nothing, and so our integral now reduces to the definite integral from 0 to 2 of x squared plus 1/4 dx. And so we can easily do that. The antiderivative of x squared is 1/3 x cubed. The antiderivative of a 4th is 1/4 x. So that's to be evaluated from 0 to 2. And of course, that we could put x equals 0 to x equal 2, but it's unnecessary now. We only have one variable left. So we put the upper value in, 1/3 times 2 cubed plus 1/4 times 2. Subtract what we get by putting in the lower value. Well, that's obviously 0. And so we have 8/3 plus a half, which is 19/6. And so that calculation has given us the value of the double integral. On the other hand, the double integral could be worked in the reverse direction. So let's look at that next. Well, let's look at this again. Our double integral over the rectangular region, capital R, of x squared plus y cubed dA, we calculated as the integral from 0 to 2 against dx of integral 0,1 x squared plus y cubed dy. So Frobenius theorem tells us that, in fact, we can reverse the order. So reversing the order of an integral is often useful because sometimes the integral is easy to calculate in one order and virtually impossible in the other. So now, instead of integrating against y for given x and then integrating the result against x, let's integrate against x first. That will be the inner integral, and so our range of x values is 0 to 2. And then that result will be integrated against y over the range of y values, which goes from 0 to 1. So now we're going to do it in this alternate order. So we have the integral from 0 to 1, integral 0 to 2, x squared plus y cubed dx dy. And so now we're going to anti-differentiate with respect to x, thinking of the y as constant. So now when I anti-differentiate x squared with respect to x, I'm going to get x cubed over 3. And when I anti-differentiate y cubed with respect to x, I'm just going to get y cubed x. And so, remember, our inner integral is against x, so our limits here are on the x. And so the evaluation here of this antiderivative with respect to x goes from x equals 0 to x equal 2. And now this result is being integrated from 0 to 1 against y, because notice once I've put in these values for x, the result will be a function of y alone. So now let's actually do the evaluation with respect to x. That is, when I put x equals 0, I'll get nothing, so all I have to do is substitute x equal 2. So the first term is 8/3 plus, and now we have 2y cubed. And so that's integrated against y. That is, we now have a function of y to be integrated, the definite integral from 0 to 1. The antiderivative of 8/3 with respect to y is 8/3 y plus the antiderivative of 2y cubed is 2y to the 4th over 4, and that's to be evaluated from 0 to 1. And so notice when I put y equals 1, this first term just becomes 8/3. And when I put y equals 1 in the second term, I get 2/4 or a half. And so putting in 0, of course, for y gives nothing. And so I'm back to where I was before. Remember, that is 19/6. So either way we work it, in either order, when I look at this original double integral that we're dealing with, what I have is the value 19/6 either way we do it. In other words, we can integrate with respect to y, thinking of x as constant first, and then integrate the result with respect to x, or we can integrate with respect to x first, thinking of y as constant, getting a function of y, and integrate that result with respect to y. That's Frobenius theorem. Well, double integrals have many of the properties that ordinary integrals do. For instance, if I'm doubly integrating a sum or difference of terms, I just do it term-wise. Likewise, a constant multiple of the integrand can be pulled completely out of the integral. On the other hand, when we're using Frobenius theorem and we've taken our double integral and represented it as an iterated integral, we can apply some of the similar properties of single integrals to the iteration, and they may not be quite as obvious as you first think. So let's look at one of these things. For instance, suppose I have an iterated integral, and of course my limits on the inner integral will be functions of the variable that's integrated last. In this case, so I'm integrating against y first and x last, and so my y limits of integrations are functions of x. But if I look at that integrand and I see, in fact, it's a function of x multiplied by some function of two variables, because this inner integral is really an integration against y with x being held constant, that f of x in the inner integral is just a constant and can come out. And so, in effect, I can simplify this iterated integral by pulling the f of x out of the inner integral, and now I can simply concentrate on this somewhat simpler integration problem. Now, this takes a particularly interesting form in the case where we're integrating over a rectangle. For instance, suppose my integrand itself is a product of a function of x alone multiplied by a function of y alone. Well, now I can pull the f of x out of the inner integral, and I've got the integral from a to b of f of x times the integral from c to d of g of y dy. Well, notice there's no x appearing in this expression. In fact, it's just a number, so it is a constant for the integration with respect to x. It can be pulled out completely, and so the iterated integral, in fact, reduces to just a product of two ordinary one-dimensional integrals. In other words, you integrate f of x from a to b, and you integrate g of y from c to d. Well, let's look at an example how we can use this to advantage. Let's calculate the double integral over the rectangle R, which is x going from 0 to 2, y going from 0 to 3, of the quantity y e to the quantity x plus y squared. Well, the first thing to notice then is that our integrand can be broken up because e to the x plus y squared is e to the x times e to the y squared. And so when I write this as an iterated integral, it becomes integral from 0 to 2 of the integral from 0 to 3 y e to the x e to the y squared dy dx. And notice this e to the x can be pulled out of the y integration. So we get the integral from 0 to 2 e to the x. And then what's left, the y part of the integral, has no x in it at all. So we have the integral from 0 to 3 y e to the y squared dy. And that's integrated against dx. You see, that's just a constant. So in effect, we can pull it out, but I'm going to pull it out to the right. And so I have that simple product of two ordinary integrals. And that's just an ordinary integral in the sense of basic calculus, and that's the same thing. In other words, we're now not really involved with double integration problems anymore, or even iterated integral problems. And so these are just individual integrals to calculate. Well, let's come back here and calculate them. The integral from 0 to 2 of e to the x dx, well, the antiderivative of e to the x we know is e to the x. Evaluated from 0 to 2 is just e squared minus 1. The integral from 0 to 3 of y e to the y squared dy is a little harder to calculate. Remember, that's an easy substitution. Set u equal to y squared. Du would then be 2y dy. And so consequently, dy is 1/2 du. You can think of dy as being 1/2, or rather y dy as being 1/2 du. So here's the y to go with the dy. And so this together with the dy is 1/2 du. And so we have integral e to the u du, because we replaced the y squared by u. Now, our limits, when we substitute, can be changed to limits in terms of u. When y is 0, u is 0, but when y is 3, u is 3 squared, or 9. And so to integrate e to the u from 0 to 9, that's just e to the u. Antiderivative of e to the u with respect to u is e to the u. And so, well, we have the 1/2. Can't forget that 1/2. And so we have 1/2 e to the 9th minus 1 for the second integral. And so our whole integral then, our double integral over our rectangle of y e to the x plus y squared against area is e squared minus 1 times the quantity e to the 9th minus 1 over 2. And of course, if we calculate this with our calculator, we find it's about 25882.33 approximately. That's 25,882.33 approximately for the double integral of y e to the x plus y squared dA. So in any case, what this illustrates is you want to watch for the case where the integrand breaks up as a simple product of a function of x and a function of y, because then it's easy to make everything reduce to ordinary one-dimensional calculus in the case where the domain of integration, the region R, is a rectangle. When we use Frobenius theorem to reduce a double integral to an iterated integral, the thing that we actually have to anti-differentiate first will depend on our choice of what the inner integral is. In other words, you've got two ways to go, and these can be very different as far as actual computation and anti-differentiation problems are. And so, in fact, sometimes one way is easy and the other way is virtually impossible. Let's look at an example. Here, I've pictured a region of integration. That's the region capital R for x between 0 and 1, and for each x, y is restricted to be between x squared and 1. And over this region, I want to compute the double integral of x e to the y squared dA. So to picture this region then, the lower boundary is y equal x squared. The upper boundary is y equals 1. And so there we see it in the unit square. Here's our region of points which are above the parabola but below the horizontal line y equals 1. So if I set up the integral so that for a given x we're integrating vertically with y, the value of y goes from x squared up to 1, and so our inner integral would be the integral from x squared to 1, x e to the y squared dy, and that's to be integrated from 0 to 1 against dx. Well, notice when I look at that inner integral, the x is just a constant, and so I'm immediately faced with how do I anti-differentiate e to the y squared? In fact, that's well known to be impossible in closed form. So consequently, it doesn't have any antiderivative that you could write down or you could ever even look up in a book of antiderivatives. So consequently, let's look at the other direction of integration and try to set that up. So in that way of setting up, for a given value of y, we're going to go across this way. And where do we go? Well, notice the x starts at 0 and goes over to the outer edge of the parabola. And so we need to express that parabola now as a function of y. That is, in this range, since y is non-negative, y equal x squared is the same as x equal root y. So now, in the reverse order of integration, it becomes the integral from 0 to root y inside x e to the y squared dx, and that's to be integrated against y from 0 to 1. So let's try it in this order of integration and see what we get. So here's our integral, our iterated integral that we're working on, and so now we get to integrate against x first, and we don't have to try to anti-differentiate e to the y squared. So what will we get? Well, e to the y squared is just a constant. In fact, we could pull this e to the y squared out of the inner integral to make it easier to look at what we have to do here. So we're just integrating from 0 to square root y of x dx, and then that result is a function of y, which multiplies the e to the y squared, and then we integrate against y. So now, antiderivative of x is simply x squared over 2, and that's to be evaluated from 0 to square root y dy. And of course, when I put in 0, I get nothing, and when I put square root y into the quantity x squared, I will get the square of square root y, which is just y. This 2 can come out as a factor of a half, the 2 in the denominator, so we have a half out front, and we have y times e to the y squared dy. Well, now that's very convenient for us because, see, even though we have this nasty exponent y squared in the exponential function, right out front here we have a y which we can use to convert to substitution. So in other words, what we were going to do here is substitute u equal y squared. Then in that case, du is 2y dy. So we have 1/2 integral 0 to 1 And we need a 2y inside, and so we'll put 1/2 e to the y squared 2y dy. So these 2's cancel inside. And now here is du. And so this becomes integral from, well, what do we have on our limits? When y is 0, u is 0. So our lower limit is still 0. And when y is 1, 1 squared is 1, so our upper limit is still 1. Inside here we have 1/2 e to the u du. And so consequently, this 1/2 comes out, we have 1/4 integral from 0 to 1 e to the u du. Antiderivative of e to the u is e to the u, and so naturally that's just 1/4 e to the u evaluated between limits 0 and 1, which is of course just e minus 1 over 4. And so that's the final answer to this double integral. In other words, because of the fact that we could reverse the order of integration using Frobenius Theorem, the reversal of the order of integration allowed us to integrate the other term in x that we could anti-differentiate, and very happily it happens to give us just what we need in order to use substitution on the integral against y. You see, so when you are faced with a double integral, if at first the order in which you set it up doesn't succeed, or even if it starts to look like a mess, it's a good idea to try reversing the order of integration to see if you don't get a good simplification.